Hi, welcome back. My name is Attila Börös. This is already the ninth lesson in our solar energy course. In the first chapters, we learned about the sun, the sunlight, its effects, the history of using the solar energy. In the last videos, we saw how can be solar energy converted to heat energy, and my colleague was talking about how can we convert the solar energy into electricity. And last time I started to explain the different solar cell technologies. There are lots of different technologies and still new ones emerge. The solar industry is a quickly developing sector with plenty of new investments and research. I won't try to cover all the solar cell technologies, just most of them which are available today. This is a huge topic, so we need 3 videos to cover them. This is already the second one. In the first one, I was talking about the basics of PV cells. We saw how can we link the solar cells, and we started to evaluate the different PV technologies with the most common type. This is the silicon-based solar cell. We will proceed on this train of thought and will discover the rest of the solar cell types. In this video, we will see the thin film technology cells and the group 3 to 5 PV cells. And finally, as a relaxation, we will talk about the loss mechanism in solar cells. You know already this slide. This chart is about the multitude of solar technologies. On the left side of this slide, you can see the most common group, the silicon cells. The previous video was about them. This group can be further divided to crystalline and thin film silicon cells. These also have subcategories like single and polycrystallines. The second big group contains the thin film technologies like cadmium telluride and copper indium gallium diselenide CIGC cells, and the group 3 to 5 PV cells like gallium indium phosphorus and gallium arsenide cells. Today we will check these ones. And for the next video, only the third generation solar panel cells remains. But don't worry, this group is a continuously expanding one, so the available time will be filled. A thin film solar cell is one of the newest kids in the neighborhood and is still in a developing stage of technology and innovation. In a thin film cell, the semiconductor layer is only 1 to 10 microns compared to 200 to 300 microns in the crystalline versions. It is created by depositing a thin but expensive semiconductor on a cheaper glass substrate. Their advantages are they require less semiconductor material and they are cheaper to produce because the glass is cheap. Among their disadvantages, there are that to manufacture good films is difficult, and therefore they show lower efficiencies. Because of this, they have been put to use in photovoltaic power stations, as an integral part of a building, and in a small-sized solar systems. If we make a comparison among the crystalline versions and the thin film technology cells, we will see that both has its role and place in the solar industry. If we remember the previous video, the first thing coming in mind about the advantage of crystalline silicon cells is its higher cell efficiencies. Therefore, they require less surface area for the same power output, so for residential areas, that is the best choice. They are the oldest technology, so they have well-established manufacturing technology. During the years, they proved their durability as well. This we can state about the new technologies. When we analyze the thin film cells, and it comes to comparing the lifespan of thin film solar cells with the poly or monopanels, they rank lower than these two and have shorter period warranties. They are less efficient than crystalline silicon. These panels have an efficiency rate as low as 79% only. One of the main deterrents in using these cells is that they require a lot of space, which becomes a problem for most homeowners going in for residential solar system installations. They are a good options if there is no space constraint for setting up the solar system, for example, in a solar farm. But let's see their advantages. They have a wider spectral response in sunlight wavelengths, so they can utilize rising and also setting sun's energy. So they are more efficient at low irradiance level. They are more tolerant of shading issues. The crystalline versions aren't grateful for partial shading. The manufacturing process of this type of solar panels is relatively easier and involves depositing one or multiple films of photovoltaic amorphous silicon or other materials onto a substrate. This process requires less material, there is no wastage, and therefore the thin film solar panels can be made in bulk for a lower price. A unique feature offered by these cells is their flexibility and lightweight, which makes it possible to use these cells in multiple applications. Thin film solar cells are less affected by high temperatures. As I mentioned before, the manufacturing process of thin film solar panels is relatively easier and involves depositing one or multiple films of photovoltaic materials onto a substrate. The technology depends on the type of material used to dope the substrate. In light of this, there are the three thin film technologies: the amorphous silicon, the cadmium telluride, and copper indium gallium diselenide. We are still by the silicon, not by accident, because silicon is available and unlimited. It is the second most element of the Earth crust. Anyway, do you know which is the first one? With its 46% in the Earth crust, oxygen is the most common element. The first thin film technology we will talk about, and the first one to be developed, was amorphous silicon, wherein silicon was randomly deposited onto a substrate, as opposed to the regular crystal lattice seen in wafer crystals. As you see, amorphous means there is no definite arrangement of atoms or no definite structure. In this case, rather than coming from a crystal structure, these cells are created from a thin layer of silicon atoms. The efficiency of amorphous cells is much lower than that of the previous cell types. As a result, they are used mainly in low-power equipment, most often in small solar panels, such as those in calculators or gather lamps. But recently, amorphous panels are increasingly used in larger applications as well. The panel is formed as one piece, and the individual cells are not as visible as in the other types. The efficiency of amorphous panels is not as high as those made from individual solar cells, although this has improved over the recent years to the point where in some cases they can be seen as a practical alternative to panels made with crystalline cells. Amorphous silicon cells are made by evaporating silicon onto a glass base. As we will see soon, this causes more random orientation in silicon atoms than in the crystalline versions. Because the non-crystalline allotrope of silicon with no definite arrangement of atoms, more electrons not bound to silicon atoms. These unbonded electrons attract impurities and degrade the electrical performance of the cell. Hydrogen is often added to the material to activate the dangling bonds. As you see here, in amorphous silicon cells, there are no structural uniformity like in other silicon solar cells. The less regular arrangement of atoms leading to dangling bonds, and to offset this, as I said, hydrogenation is used. The result is that the hydrogen atoms combine chemically with many of the dangling bonds, essentially removing them and permitting electrons to move through the material. Amorphous silicon is obtained by depositing silicon film on the substrate like glass plate or plastic. As you see, this is the thickest layer in the cell. The optical structure of the solar cell included a half millimeter thick fluoride doped tin oxide as front transparent conductive oxide, TCO. Below it, you find the thin p-type layer of doped amorphous silicon. The age after the silicon means the hydrogen. Then a bit thicker I layer of silicon and an N-doped amorphous silicon layer. Below that, another layer of TCO and a metal black contact. So the layer thickness are less than 1 micron. The thickness of a human hair, for comparison, is 50 to 100 micron. These products require higher currents than small cells, and it was found that an additional layer called a transparent conductive oxide, TCO, could facilitate the movement of current across the top of the cells instead of a metal grid. One such TCO, tin oxide, was available for other uses, for example, thermally reflective windows. Made more conductive for PV, tin oxide became and remains the norm in the cadmium telluride photovoltaic modules. Amorphous silicon thin film solar cells are comparatively less costlier and easily available around. The efficiency of these cells varies from 4 to 8%, but it is improving. You can see here some of the advantages of it. For example, it absorbs low and high intensity light as well. It is partially shade tolerant. For processing, less semiconductor is needed, therefore it is cheaper. High temperatures adversely affect crystalline silicon cells, but it doesn't significantly reduce amorphous silicon cells' performance. And it is more effective in hotter climates. It has more or less the same disadvantages than all the other thin film cells. The main one is the lower efficiency. Long-term degradation of material under sunlight is based on experience. The production is not too complicated, but requires hazardous gases. These cells require less installation time and require much larger space for same output. Area required for 1 kilowatt solar panel is 13 to 20 square meters. Based on global installed capacity, gallium telluride is the leading thin film PV technology. The main attraction of cadmium telluride for solar cells applications is their high bandgap, which is in the perfect range for high efficiency single junction cells. Cadmium telluride technology is based on the use of cadmium telluride in a thin semiconductor p-type layer and cadmium sulfide as n-type layer designed to absorb and convert sunlight into electricity. On a life cycle basis, cadmium telluride PV has the smallest carbon footprint, lowest water use, and shortest energy payback time of any current photovoltaic technology. Cadmium telluride solar cells use technology which produces solar cells at a lower cost as compared to its counterparts. The payback time for these cells is also less than a year. And in multi-kilowatt systems, it is the only thin film technology with lower cost than conventional solar cells made of crystalline silicon. For making a practically economically viable PV system, cadmium telluride is the winner, as it is 50% less costlier than conventional silicon cell, and its efficiency rises from 9 to 16%. Cadmium telluride thin films had a peak recorded efficiency of more than 22%. I said many times the efficiency values of the different cells, but what does it mean, that 16%? It is the percentage of photons hitting the surface of the cell that are transformed into an electric current. Area required for 1 kilowatt cadmium tellur solar panel is 11 to 13 square meters. Cadmium tellur photovoltaics are used in some of the world's largest photovoltaic power stations, such as the Tropaz solar farm, with a share of 5.1% of worldwide PV production. Cadmium tellur technology accounted for more than half of the thin film market. The main aim behind using solar power technology is to protect the environment. This type of solar panel does the best as a manufacturing process of these cells requires a very little amount of water for production. But on the other hand, one feature that makes cadmium telluride solar cells a little less attractive is its toxicity if it's ingested or inhaled. There is also a disadvantage that it requires high processing temperatures. Cadmium telluride is unstable, therefore it will degrade. Cadmium telluride is unstable, therefore it will degrade faster, especially sensitive to water ingress. On this slide, you can see the cadmium telluride cross-section. Each cell comprises a junction of n-doped cadmium sulfide, known as the window layer, on the top of the p-doped layer of cadmium telluride, known as the absorber. A transparent conductive front contact covers the cadmium sulfide, while the cadmium telluride is in contact with the conductive real surface substrate. The cadmium telluride technology utilizes high throughput fabrication techniques, for example, closed-space sublimation, requiring high process temperature in the region of 600 Celsius. One of the issues with the cadmium tellur cells was the cadmium is toxic and costly to dispose of. To prove its safety, in 2004, Israeli researchers made a small-scale test with the cadmium tellur modules. Tests were performed up to 1100 Celsius of small-scale glass encapsulated modules. It is proved that 99.5% cadmium remaining in module. The minimal loss was through end of exposed end of module. In real world, modules loss expected to be less than 0.04%. So the overall risk is very low. The next thin film solar cell is copper indium gallium diselenide. CIGC is the semiconductor material composed of copper, indium, gallium, and selenium. It has been labeled by experts to be the solar technology of the future. The technology allows us to achieve efficiency values comparable to conventional multicrystalline silicon technology. It has extremely good light absorption, 99% of light absorbed in the first micron. The addition of gallium boosts its light absorption for the whole solar spectrum. So far, scientists state that there is no performance degradation over time. It has much higher efficiencies than other thin films, around 19%. The basic structure of CIGC thin film solar cell can be seen on this image. The most common substrate is soda-lime glass of 1 to 3 mm thickness. This can be seen below. This is coated on one side with molybdenum that serves as a metal bed contact. The heterojunction is formed between the semiconductors CIGC and zinc oxide, separated by a thin layer of cadmium sulfide and a layer of intrinsic zinc oxide. The CIGC is doped p-type from intrinsic defects, while the zinc oxide is doped n-type to a much larger extent through the incorporation of aluminium. As always, we evaluate its pros and cons. First, let's see the advantages of CIGC. The active layer CIGC can be deposited in a polycrystalline form directly onto molybdenum-coated glass sheets or steel bands. This uses less energy than growing large crystals, which is a necessity step in the manufacture of crystalline silicon solar cells. One environmental advantage of CIGC solar cell technologies have over cadmium telluride solar cell panels is that it uses a much lower level of cadmium in the form of cadmium sulfate. In some designs, sometimes zinc is used instead of cadmium sulfate altogether. Like cadmium telluride panels, CIGC solar cell panels show a better resistance to heat than silicon-based solar panels. The spectrum absorbed by mono, poly, or amorphous silicon cells ranges only from 400 to 700 nanometer, with the absorption range for CIGC cell is from 300 to 1300 nanometers. This means that the effective time for generating power is much longer each day for CIGC than other technologies. The electron power generating process keeps working from morning to sunset. CIGC modules have excellent performance during low light, cloudy, or hazy conditions. CIGC panels are activated by the presence of a low level of photons. They are less dependent on direct sun radiation or the position of the sun in order to function. Even though the current in use CIGC PVs efficiency may be lower than that of silicon-based modules. CIGC panels absorb more sunlight per day, and so they produce more energy in total each day. Silicon-based modules have a degradation factor 1–2% in kilowatt output per year. CIGC modules provide consistent kilowatt per hour output each year with little or no degradation. In the other column, you can see the disadvantages of CIGC. Like all thin film solar panels, CIGC panels are not as efficient as crystalline silicon solar cells, for which the record efficiency lies at 24.7%. They are, however, the most efficient of the thin film technologies, so far being able to produce solar panels at prices that can compete with polycrystalline or cadmium telluride panels has not been possible. There is growing concern by some parties that the cost of fabricating the product makes it difficult to be competitive with current grid prices. It may take several more years to solve the manufacturing problems and bring the production cost in line with the other leading producers of solar panels. After finishing the thin film cells, it's time for a quiz. Comparing crystalline silicon and thin film cells Which is better, efficiencies? The crystalline silicon. More efficient and low irradiance level. Thin film. It has nature technology. Crystalline silicon. Durability. Crystalline silicon is better. It has a wider spectral response. The thin films are better. They are more tolerant of shading issues. Also, thin film is better. Use less energy and material to produce. Also, thin film is better. More flexible. The same thin film. Require less surface area. It is the crystalline silicon. Upward trends in energy cost are a powerful motor in the development of new energy sources and reduce relative cost of a range of technologies. This is the case for the 3 to 5 semiconductor compounds, which are traditionally an expensive photovoltaic technology, whilst also being the most efficient, with corresponding advantages and disadvantages. As you see in the right side on periodic table, these cells consist of compounds of group 3 to 5 elements. Compound is a material that combines multiple elements in a single structure, not just a mixture. It is used extensively in the electronics and optoelectronics industries as well as space batteries. These are excellent but very expensive solar cells. They are a big potential in this group, and one can create multi-junction cells also for higher efficiency. But first, let's see the single junction cells. These cells are made from combination of two materials, gallium arsenide and indium phosphide. In research tests, the best efficiency is at 27.6%. If you remember the very beginning of this course, I explained that because of the losses in the atmosphere, the incoming 1360 watts per square meter energy will decrease to a maximum 1000 watts per square meter energy hitting the surface. If we consider this value of sunlight energy, it produces 276 watts of usable power per square meter. Let us see the arguments for and against it. Principal among the disadvantages are relatively complex synthesis and device fabrication, and corollary issues such as availability of relatively rare elements, indium and gallium. These 2 points are largely responsible for the higher cost. Among the advantages, on the other hand, are a number of materials characteristics which make 3 to 5 solar cells the most efficient photovoltaic materials available at present. The principal reason for this is a flexible combination of a range of materials from binary to quaternary compounds with a corresponding flexibility of bandgap engineering. Because its low weight and its resistance to damage from cosmic radiation makes it an excellent space solar system. Here you can have a glimpse to the multi-junction solar cells. As the researchers explain, multi-junction solar cells are one of the most promising devices for efficiently converting sunlight into electricity. In multi-junction solar cells, each junction or subcell absorbs and converts sunlight from a specific region of the spectrum. The subcells can be stacked on top of one another so that sunlight first strikes the highest bandgap subcell, which is tuned to light with the shortest wavelengths or highest energies. The longer wavelengths pass through the first subcell and strike the lower bandgap subcells. This arrangement offers a significant advantage over single-junction solar cells, which have a maximum theoretical efficiency of only 34%. In theory, an infinite junction solar cell has a maximum theoretical efficiency of almost 87%. But to approach this level, multi-junction solar cells not only need multiple subcells, but optimal semiconductor materials for the subcells to provide a combination of bandgaps that cover as much of the solar spectrum as possible. So they have very high efficiencies, but they are very expensive. Therefore, they are widely used for space applications. Here you can see a three-junction solar cell cross-section. Above in these devices are a high bandgap top cell to absorb high energy photons while allowing the lower energy photons to pass through. A material with a slightly lower bandgap is then placed below the high bandgap junction to absorb photons with slightly less energy, lower wavelengths. As the light hits the surface of these cells, each junction absorbs what it can and lets the remaining light pass on to the next junction. You can see the blue subcell above with the biggest bandgap. Below it, the green one, and below the orange one with the lowest bandgap. As I said on the beginning, after covering this type of cells as a relaxation, we will see something else. The remaining third generation cells will be the topic of the next video. We always compare the different cells by its efficiencies. But what are the losses which degrade the output values of the system? We will check these ones. As you see, the losses can be categorized to optical and electrical losses. Both of them can be further subcategorized. Let's start with the right side. Electrical losses have detrimental effects on both the current and the voltage of the solar cell. These losses may be conditionally divided on two large groups: losses due to electrical transport, ohmic losses, and recombination losses given by various recombination mechanisms. The ohmic losses include electrical resistance to transport of charged carriers within dot regions of the device, emitter and base, resistance of a p-n junction, a contact resistance on the borders of the semiconductor and metal collectors, and the resistance of thin metal films of the collector system. The recombination losses are defined by various processes in the semiconductor: a radiative recombination, luminescence, Auger recombination, recombination on the semiconductor defects and impurities, and surface recombination. Optical losses reduce the level of solar radiation by reflection and shadowing of the irradiating light. A spectral sensitivity of various semiconductors insert significant part of optical losses. All photons with energy lower than the semiconductor bandgap cannot produce electron-hole pairs and spread through the semiconductor. Photons with energy that use more than the bandgap generate excited charge carriers which transfer additional energy to the semiconductor material, the thermalization process, and heat up the photovoltaic device. This increasing heat decreases the cell efficiency. Also, the quantity of photons with various energies is defined by the solar irradiation spectrum, which reaches the solar cell. The right side of the diagram is not the topic of this course, So we will evaluate only the optical losses. Do you remember from this slide from the second video? Except the black hole, everything has albedo. The brighter an object, the more light it reflects back. What causes reflection on a solar panel? At the front of the solar cell, there is a circuit path which works as a metal contact. This metal part has to be very small, but if it's too small, then transition resistance between the metal and the semiconductor is very high because they are inversely proportional. So, although it is a small surface, but it is shiny. And apart from its reflection effect, it also casts a shadow. But for shading losses, a bad system placing is much more dangerous. We know that bare silicon is highly reflective, and most of the residential solar system consists silicon solar cells. So the cell itself reflects light. And of course, the front of solar cell, the glass layer, can reflect a lot. And because of the different refraction index between the air and the cell, there is reflection on its surface. Refraction can be seen in the right bottom corner. This picture can be familiar from the previous videos as well. The angle of incidence is highly affecting refraction. The higher it is, the less refraction is occurred. It can be achieved with tracking systems. So when light striking the surface, what can happen with it? The light can be absorbed and converted into electricity. This is the good scenario. It can be reflected. This is optical loss, so we don't like it. And it can be transmitted. Optical loss if escapes. How can we decrease of these optical losses? The transmitted loss can be decreased with multi-junction solar cells. Metal contact on the surface can be reduced in size, but at the expense of resistance growth. And the front protective layer is also a must, but with different techniques, its albedo can be decreased. For example, with texturing and with anti-reflection coating. Here you can see the texturing. Using it reduce the reflectivity of the surface of waters by forming microscopic structures. It works mainly for single crystal surfaces. As you see, the pyramidal surface reduces total reflection by reflecting light into another pyramid instead of a wave. So it increases the chances of absorbing the light. Using it, the average 30% reflection from polished silicon reduced to 10% from textured silicon. The other widely used method to decrease reflection is anti-reflecting coating. Finished PV cell is coated with a material to reduce the amount of reflected light, just like eyeglasses. This is usually used on cells unsuitable for texturing. It is quite useful because it can reduce reflection to 5%. Here you can see some anti-reflecting coating materials: silicon nitride, silicon dioxide, and zinc oxide. There is a short quiz about the second part of today's video. The first question: what is the main advantage of a multi-junction solar cell? Each junction has a different bandgap energy, so each will respond to a different part of the solar spectrum. So it utilizes much more energy than a single junction cell. What type of losses occur when light hits the surface of a cell, and what can be done? Reflection. Texturing the surface and anti-reflecting coating. refraction, optimizing the angle of incidence with tracking devices, shadowing, minimize front contact, but not too much, because to do so the resistance will increase, and also a good idea to not place the solar system below a tree. Unabsorbed radiation using multi-junction solar cell. In the evaluation of the different solar cells, the third generation was not on the operating table yet. For the next time, this group will be our topic. This is a big and continuously expanding group, so we will mention only the more significant ones. See you next time. Bye.